I'm super glad to introduce our SPCL broadcast series, which is actually a seminar series we'll be running in the coming months. Every 2 weeks, we will have a speaker. Fortunately, we were able to convince Satoshi, it didn't take too much convincing, to give the inaugural talk, and I will give to Nikolai, who's organizing the series, to introduce the speaker. Thank you.
Okay, welcome everyone. So Satoshi Matsuoka, our inaugural speaker, the director of the Riken Center for Computational Science and a specially appointed professor at Tokyo Tech. Among his many accomplishments, he's won both the Gordon Bell Prize and the Sidney Fernbach Memorial Award. He's also led the design of the Tsubame series of supercomputers. My personal favorite here is the Tsubame KFC and the new Fugaku supercomputer, which we'll hear more about now. Thank you, Satoshi.
Okay, and thank you very much for the invitation to talk. And also thank you everybody for participating. I know it's hard times, but I'm glad we have this mechanism by which we can still communicate and exchange research ideas and move forward in science. So anyhow, I'll give my talk on Fugaku, which some of you may have heard, but it'll be good to sort of give a first-hand account on how it was built, how it was designed and built, and what we do with it, and especially, and also I'll mention a little bit about what we do with AI, especially what we think about dealing with very large-scale AIs on these machines, because now another trend is for big, also for like big global hyperscaler cloud data centers to also facilitate very large machines, AI machines. So firstly, just to advertise, and those of you who are interested in coming to Japan once this COVID-19 stuff is over, we're running this research lab. This is one of the 12 Riken, our CCS is Riken's Center for Computational Science. Is one of Riken's 12 research centers. We also the National Flagship Center for this type of computing. So it's like CSCS in Switzerland. We have 18 research teams, more than 4 operation teams, actually now 5. And we have 200 FTEs plus lots of visitors, so we have several hundred people here. And what we do is we study science of computing, by computing, for computing. Science of computing, we study computing as a discipline. That's our namesake. And computer science, not much of what Torsten, people like Torsten and I have been doing for many years. Science by computing is utilizing the power of computing afforded by these research into your applications, answering tough questions that society needs, like the environment, energy, disaster, climate, etc., medicine. And we have research, half our research team is doing that. And that's how one of the benefits of having a very large machine. And if we have science for computing, there are other branches of science that actually collaborates with us to move science forward, materials for new semiconductors, photonics, etc. So all combined, we are basically the pinnacle research lab, research portion is we're the pinnacle research lab, totally focused on high-performance computing. And we're soliciting interns, we're also soliciting researchers, full-time researchers, we're also soliciting senior members. So if you have any interest in working in Japan at some function for a couple of months or for years, you're very welcome. We have an abundance of research staff that are foreign. And Riken's one of the best institutes to accommodate foreign talents. Also in COVID, so we can eat COVID if you can afford it every day. It's hard to afford it. So we have lots of research results under our belt. We've been awarded various accolades. We do very large scale simulations of things like earthquakes or combustion, etc., much like what the EU labs do and so forth. And one of our missions is to design next generation, do research on and design next generation flagship system for Japan. And used to be the K computer, now it's Fugaku and Untitled Chapter. That would be the main part of the talk. Just a little review on K. It was decommissioned last August in 2019. It was at one time the fastest supercomputer in the world when it was commissioned, according to the top 100. But it won other accolades too, like HPC was #1, was #1 Graph 500 until it retired. It won several Gordon Bell prizes. So it was a machine of the time, and it had its benefits and drawbacks, but one cannot deny that basically it modernized supercomputing through massive parallel computing. It had 88,000 nodes and so forth, and almost 700,000 compute cores. So it really opened up the massive parallel computing for Japan, for the Japanese community to move on to that style of computing. But like I said, it was decommissioned, and we had a big ceremony. That's the President Enrique giving a speech in front of all the many politicians. And it was a very decorative shutdown ceremony. Now, so K was basically focused on basic science and simulation. And like I said, modernized Japanese supercomputing through massive parallel era. But what we really want to achieve was go beyond that, because large-scale simulations are transient. We may get great results, but just like any basic research, at least success is not to take a chance. And it's difficult to justify that type of instrument to fund it. Because K costs about $1 billion US dollar, which is about 1 billion Swiss francs. That's very expensive. So we really had to basically, for the next generation machine, we had to have a machine that would drive the impact beyond just basic science. And that meant that we had to make much more general purpose. But also we had to respond to many of the application science requirements, and to, not just to the peak flops, but also to the very broad industry. And also we had to have some computer science significance as well. So you have to answer many, many requirements well beyond what K had. Oops. So Fugaku, it's a namesake for Mount Fuji. It's an alternative name for Mount Fuji. We usually call it Fujisan, maybe Mount Fuji, but Fugaku is an alternative name. And for Mount Fuji, and just like Mount Fuji, Fugaku is sort of representing the idealism of supercomputing that we see, that it has a very high peak. So it can support these latest and greatest grand challenge type of applications, but also it has a very broad base, and that's why the Mount Fuji is so beautiful. It's a standalone mountain, so it's very broad base. And for supercomputers, its applicability and capacity, meaning broad range of applications, not just restricted to traditional simulation, but also things like data science, AI, also broad user base from academia, industry, and also the cloud startups. We want cloud people to adopt the technology, not just some narrow sets of advanced academics. I'm sorry to send some Japanese in this slide. So I discovered a few moments ago this was not translated, but just give you but it's not very significant. So we really developed this machine to be applications first, and but it was a huge national challenge, was almost a moonshot. Because compared to K, which was the development target was enormous. However, it was still doable. So in fact, if you look at K's technology, it was very conservative in its design. And I have a big discussion with Richard about why are you guys building such a conservative machine? They said, well, we can't fail because we are a national project. And my answer was, no, that's not what national projects would be. National projects would be like Apollo program. Should be a moonshot. Should be something that's not achievable with just a single company. But the whole community comes together to do high risk development. And so K was not like that. Fugaku was. And the reason we had to take such high risk was so what we did was to, as I will describe, we got the community together. And we did an assessment of the requirements, and I was part of it, of what kind of machine we had to build. And it turns out that projecting forward, all the like product roadmap, that, let's say, Intel's and so forth, all the way up to 2020, and it was just very evident that nobody would have the hardware or the chips required to satisfy the goals. So we had to build our own, of course. That's the nature of a national project. But we had to build we were going to do it anyhow. But we set this almost unattainable target. So would turn out to be the end result. So the chip we got, basic effects, which is according to our benchmarks and most HPC workloads, about 3 times faster than comparable Intel processor, or 1/3 the power efficiency, 1/3 the power of the 3 times power efficiency. But even satisfying those types of power of performance requirements, user requirements, not the goal. These were not something that we got lucky to ever have. We had to achieve those goals, but we had to have the chip be general purpose. So it's an ARM chip. So it runs every application run on your smartphone or ARM PC, or you just recompile most of practically all of the x86 codes will run on this platform. And the acceleration, also we needed acceleration feature just much like GPU for AI. So we actually put those into. So when you think of the capacity of this machine, it's each of the chip is about 50 to 100 times faster than the smartphone chip for HPC workloads. So it's about equivalent to about 20 million smartphones, which is about the number of smartphones sold in Japan over the course of a year. Or so that's 2 or 3 times the entire. So we have 2 or 3 Fugakus. It'll satisfy most of the IT requirements of Japan as a country, which is still the 3rd largest economy in the world. So, and then, but again, this was achieved with very tight collaboration between what it says on the left-hand side is science of computing or computer science, and these are people like us at Weekend, and also at Fujitsu, and also all the computational scientists, the entire community. So this was done in about 10-year time frame. In fact, this project started back in 2010. And we did lots of preliminary studies, including very detailed analysis on the requirements of machine that would become exascale in somewhere around 2020 timeframe. But also not just to say we achieve exaflops, unlike other countries, but rather to say, what do we mean by exascale machine? And we tried to do a very detailed analysis of many application areas, and to say what are the application requirements, what kind of groundbreaking science that would be possible with that machine and that capability, and what kind of compute would you do? Well, what kind of algorithm would you run? We asked all those tough questions, and then it became officially a national project in 2014, and then took about 5-6 years to build, to design and build, and here we are today. Became number 1 on all the benchmarks, but that's the fact that it became number 1 on all the benchmarks, not just on top 500. It was very important to us, although it's being an application first machine. And I'll tell you about that later, what that's saying. So like I said, it was by collaboration, and one of the things we did was to set the goal to say, for the 9 representative applications out of representative domains, we would achieve somewhere close to 100 times speed up on some of them, and close to that, somewhere like 30, 40, 50 times speed up the majority of the application. over the K computer, and still have ease of programming. But let me first tell you how we drive at these goals. And this is where I don't typically give a talk. But so what we did when the K was being finalized, and there are lots of political. If you look on the web, you'll see what kind of scandals that happened, or fiasco that happened at the very last stages of K development. But we came through, and the machine was there, was being installed. But then we wanted to start the next effort. Around that time, globally there were efforts being led by the Americans and also Europeans, and also to some extent the Chinese had already participated, and we were there to really think about the next machine, which would be an exascale machine. And there were things like ISP. There are a lot of efforts trying to come up with what are the architectural requirements and features, and how we achieve those goals, and what are the applications that we run. But we went back. Of course, there was a global effort, but we went and really did a really detailed analysis of what's possible, and what would be possible in 2020 and back in 2011. And we came up with 4 archetypes of machines with 4 archetypes: general purpose, capacity, bandwidth oriented. So general purpose is like what most people build today, even now. Just have a vanilla x86 chip, and just hook them up using some fast interconnect like NVIDIA. So a K computer actually is of that type as well, although it uses proprietary interconnect. Then there will be type of machines that would use very expensive memory, like as we have done for Fugaku. So we would have very fast bandwidth, but limited capacity. This is very similar, reduced memory, but this would have much more flops associated with it. So because you have more flops, but you would soon be running, not linear order algorithms, but more quadratic or even cubic type of algorithms, which of course will reduce the memory access requirements. For example, matrix multiply. So in those cases, you don't need much big memory, because if you have big memory, then your compute time will explode. So you'll be limiting the memory size, but you have very abundant compute capability. And it's very similar compute oriented. And these are sort of the distinction between these two are fuzzy, but have a little bit different memory, have reduced memory bandwidth. So then we projected using our knowledge of the device, the projected device physics, and also projected outlines of the semiconductor lithography improvements, also various vendor roadmaps and so forth. We tried to estimate what would happen if we would build these machines in, let's say, 2018 to 2020 timeframe. What would be the total CPU performance? What would be total memory bandwidth? What the total memory capacity, and vice versa, etc. And also the interconnect, we did a similar analysis, and storage as well. And it's a very the whole study was made into a white paper. And then, given this archetypes, we tried to put them on the sort of like a heat map of various applications. These cross points on the left-hand side you see are the applications, and these are the sort of measured requirements with respect to bytes per flop versus the requirements of memory capacity. So, and this is total memory capacity. So it turns out that it kind of went all over the map. Some applications required very little memory, but had very little bytes per flop requirement, but of course that meant that required significant compute. Some application required considerable memory capacity, but at the same time the bytes per flop ratio was very big. That means memory capacity requirements was somewhat falsified, because if they had very high bicycle capability, and if you don't provide it, then your runtime for the application will be forever. So you do have to use memory. So the memory capacity in any case. So we did all these analysis. This kind of came up with this map saying, here's our projected performance, but here's here's what the requirements would be if we try to satisfy the requirements that were set forth initially by the application before. There's a huge gap. So we said, okay, we've got to fill this gap, okay, for any of the and so we had to do two things. One is to figure out, can we merge these architectures? Can we streamline these architectures and merge some of the properties? Because we can't build develop four machines at the same time. Also, what are the methods by which we can try to fill this gap between performance versus the requirements versus the achievable performance that we project in 2020? The follow-on to that effort were four efforts. So we basically, out of the four, we kind of merged this reduced memory and compute oriented. We had general purpose capacity bandwidth oriented, and then we merged the last two. And then set out to have the three teams, independent teams, some from mostly computing centers and universities where we can, teamed up with vendors to do even more detailed studies on the architecture, as well as to see how we can fill the gap. And also, I co-led the application team, but of course I did the system part of it. Yokumi Tomita is now one of my PIs, team leaders at my center. He's a CFD climatologist, but he also led the effort to basically assemble a few hundred people. All of these were application people. Well, let me rephrase it. What we did was to basically say, call out to the K application teams, saying, okay, we need all of you to participate in designing our next machine. Don't send your senior people, but send people who are actually programming this stuff or developing code and doing real science. We'll put all the people in the same room, and we will assess the scientific requirements. What would not just flops, a much more detailed assessment of what kind of algorithms, what are the scientific methodologies, what are the algorithms they'll be used, they're useful, anticipate to use, and if they achieve, let's say, 100 times speed up, what would be the impactful science they can do? So we asked all these questions. And then people went discussing commonalities, consistencies, so forth, and it ended up in the 600-page report. And we still update this as we speak. You can download it. This is a May 14th version, but there's an up-to-date version, which really hasn't changed. I'm sorry for this little blemish. I didn't find ways to remove it without affecting screen capture. So I'm really sorry about that. But basically, that's the cover, and in the center, you'll see a very typical science case. So this is what it says on drug discovery healthcare. So it's all kind of the report's kind of templated per each domain. It says what are the current studies and challenges, and but if you had a, let's say, 100 times faster machine, what would you do? What are the approaches you'll be taking, and how would contribute to society? How would it change your science? And then what I asked each team to do is to come up with this chart, which says, okay, how much compute, how much bandwidth, what are the algorithms that are going to be used, and especially numerical methods. And so there's a huge table basically describing each discipline, and of course we aggregated it into one gigantic table. And then this became the basis of picking important application areas that we meant to accelerate. Okay, for that. So after that report, the government went back and said, well, okay, out of this, we'll pick 9 areas. 9 areas meaning, most of those important to society have, high societal concerns. There are 9, but they can be categorized into large ones of 5 of them. One being medical, pharmaceutical, one being disaster prevention and environment, like climate, from global warming to floods and tsunamis and typhoons, so forth, and earthquakes. One would be energy, generation, storage, and also transmission. And of course, there are many ways to do all of them, but try to cover as many as possible. And then all the industrial applications, from materials to very large-scale structures, CAE, and so forth. And then, of course, there's basic science and like dark matter science, QCD, and so forth. So that's not forgotten as well. So these were main vast priority issues. I'll just give you a little bit of flavor. So, for example, this is I'm sorry, the animation is not very smooth over Zoom. And practice is really smooth. So this is Genesis molecular dynamics. It's sort of like it's very large scale molecular dynamics. It's sort of performance-wise, it's about this performance GROMACS. Although GROMACS is excels in mid-sized proteomic structures, but this scales to bigger ones. Well, there are pros and cons. Both can think of these as being largely equivalent, and people may pick one over the other depending on their needs, but both are very optimized. But with very large structures, you don't do something like on the left-hand side with this protein, but look at this, 100 million to like billion atoms and the combination of proteins that are constantly the structure of the cell and membranes and so forth. So this ability actually is allowing us to combat the coronavirus quite effectively, turns out. But again, the target was to accelerate this to be 100 times faster than we would have capable. Another one would be climate. This is a global climate simulation. Of course, this can be applied to weather as well. But this is a sub-kilometer mesh, meaning that they can simulate clouds with using first principle physics instead of simulated modeling. So on the K, we were able to demonstrate that such a large-scale global climate simulation is possible. And of course, you need to simulate this stuff for years, and then K was just too slow to do that. So again, the goal was to speed this up by 2 orders of magnitude, so that we can get results in sensible time to see the effects of global warming. And related to that, we also wanted to tackle modern applications, big data, AI, so forth. For one example is big data simulation. So we had this modern radars, we had modern instruments, very high precision observation, and you want to be able to assimilate this with weather forecasts. Of course, it has been done, but we want to scale both the radar equipment, resolution of radar equipment, and also the simulation that we do by 2 orders of magnitude. And of course, that results in many challenges, including increase in the bandwidth. And also, you have to be able to do this simulation very rapidly. But again, this was considered a big challenge because data simulation we see as being one of the trends we see in the science that we do. So out of those 9 application areas, you see the chart on your right-hand side, Genesis, Genomon, Gamma. These are all names of applications. So each of the 9 areas were asked to just to give us just one app, and we named it co-design application, co-design app. And so, although these were, people said, can't we pick more? We said, no, we're going to just initially target 9, but so pick the representative one. And people did come up with these. And it's not to say people who, there were many other codes that run as part of application research, but these are in co-design targets, the ones we intended to optimize too. So we went back and we analyze the applications, and we looked at the architecture parameters, and also did various projective studies on the earlier version of the Fugaku. So after K, there was a machine FX10, and then Fujitsu had productized this FX100 in 2015, which, if you look in close detail, was somewhat similar to Fugaku architecture, although the ICE is different. FX100 is still Spark-based, and Fugaku is ARM-based. But if you ignore the ISA difference, and also ignore the difference in number of resources, because FX100 is about 20 nanometer, whereas Fugaku is a 7 nanometer. So there are differences like that. But architecturally, they look very similar. There are lots of similarities. Very different from K, actually. So we took FX100 as a proxy, and then we did lots of these studies, cyclic studies on determining all these parameters and doing performance extrapolated performance projections to optimize the architecture. And down the road, that wasn't enough, so we built this. Back then was called PostK. Was called PostK, so we built our own simulator. So we had its own simulator based on Gen 5. And also Fujitsu had its own, of course, in-house simulator, and we were, comparing lots of notes and performance results as opposed to what's the best way to build these. One thing that was a big question was because of course at the time both the Fujitsu and the Cray was working with the ARM to implement new scalable vector extension instruction set, which was fine, and we contributed a little too. But one of the design choice, because SVE is vector length agnostic, we had to find the ideal vector length. And not only that, ideal ways we could lay out the LUs and so forth. For example, if we had the same resources, would you be building a 1024-bit vector, or would you be building a 512-bit vector, but double pump it, much like AVIX 512 double pumping they do on Skylake Intel chip. So that was a choice, and it's not something very obvious. Performance model will not make the distinction, so we really had to simulate it. And we found that in majority of cases, 512-bit times 2 would be superior. So that was the design we went with. So there were a lot of co-design effort ongoing, and once we decided 512 times 2, then the compiler team basically went to optimize it for that, and the application team took the compiler and they optimized the code. They tried various mixed precision optimization, given as well, because there were lots of different types of precision being supported on the chip. So it was all kind of a considerable cross-pollination ongoing in the code design. So the end result is a A64FX. It's a 48-core chip, 8.8 billion transistors. So the number of transistors isn't that big, and that's the reason is, if you are in an architecture type, is because the cache on this chip is not very abundant, unlike Skylake, because we don't have L3 cache on board, and that's the reason being we judged it was not necessary to have L3 cache, rather because we were going to attach HBM directly that would serve as L3 cache. So actually, it's very logic dense. And also, if you look up the top portion of the chip, you'll see the PCIe interface. That's PCIe 3. Unfortunately, we said Fujitsu, why don't we have PCIe 4? Is that oh, it's going to be we can't finish the chip in time and so forth, and they kind of weeped and cried. So we said okay, but and there's this TofuD, which is a proprietary 60 torus interface. So it's surprisingly small, but these two components actually connect to the you don't see here very clearly, but it's connected to the ring bus that connects the 4 quadrants, or what's called CMG. So if you look at the, you'll see the 4 quadrants, CMG, and each of CMG has a HBM2 interface. But it's all, but it's not like these are separate chips, chips. Rather, everything, all the memory, the cache, everything is cache coherent. Although there are differences in performance. So exploding locality both at the cache level, but also at the quadrant or the CMG level is a very important optimization you need to do on this chip. And I'll get to this later. I'll describe this in detail over the next several slides, but the end result is we got 3 times better performance, primarily due to the integration of HBM2 for the first time for CPU. And we score, and if you're an architecture type, you can see it's not very trivial. That's not a very trivial thing to do, because it's not only you can attach it, because attaching HBM2 to a die is not all that hard, but I have to have sufficient bandwidth in the chip, and also we have to have the proper streaming capability, and also it have to be very power efficient, which is a different type of a design criteria. So compared to running Himeno benchmark, which is a very, very naive, direct solver, sort of stencil type CFD code, very, very, it's a toy benchmark, but but it still signifies the excellence of this processor. So compared to Intel Xeon Platinum 8168, which is this Skylake, but the results is not very different from a Cascade Lake as well, or AMD Rome. In that this is a 2-chip node configuration. So if you have 1 chip, it's half the performance. And this is Fugaku's ACE4FX. And this is a dedicated SX, or this NEC's dedicated vector chip with HBM. And this is NVIDIA Tesla B100. So you can see that in terms of the CFD benchmark, Fugaku chip ACE4FX, by and large is competitive, about the same. In fact, it's the best, but by and large the same as these special purpose streaming chips. And also, but about 8 times faster than Intel Xeon. But for real apps, of course, you have, there are a lot of integer operations involved, not just for computing integers, but like doing indexing for irregular meshes and so forth. And so, of course, the performance goes down a bit. But you can see that the Fugaku is about 50% faster compared to 2-chip configuration, or about 3 times faster. Okay. So this is, and then of course we would configure this, and this would kind of stack up to become the entire system. And the result of this was demonstrated on the Green 500 in November, which achieved day number 1, if you were paying attention to the list. But that itself is not very important. The importance is this. So this is plotting the gigaflop per watt performance number versus the Green 500 ranking. So you see from rank number 1 all the way up down to rank number 500. And this is a gigaflop per watt, computing. This is a LIMPAC, a gigaflop per watt, or LED composition. So the dense linear algebra is still gets some of the, you can see some of the results here. And the blue dots represent general purpose CPU based machines. And the orange dots represent GPU and other types of, a little bit more special purpose, not general purpose. Not general purpose meaning, you can't run the operating system directly, or lack a lot of the general purpose features, or a very slow integer. You don't have the very fast integer execution units, out of order integer execution units, just like modern standard CPUs. So if you look at this, the list is dominated by these orange dots, meaning that this blue dot. Aside from blue dot, the general purpose CPUs were not good. In fact, that was the understanding of the industry and the community, that you had to have a special purpose, very flops, well, I would say flops-oriented or LU-oriented architecture in order to achieve very high efficiency. But we disproved otherwise because, again, we became number one. And again, but it's not so much the matter that we number one. Again, it's what matters is we're comparable to the top performances that are exhibited by things like the V100. And also, the top Xeon machine is this 5.8 gigaflop per watt, which is about 1/3 the performance of the FX prototype with what became Fugaku. It's the same hardware. So, it's 3 times better than a comparable Xeon machine. Okay, so how that's achieved? Well, so from a top level view, Fugaku's processor is, on one hand, is very much like a mini core ARM CPU, like I described. 4 quadrants. There's a network on chip, which is actually a ring bus, and then we have 13 cores each. You can count 13 here, actually, but one core from each of the CMGs or the quadrants is reserved for the operating system to reduce operating system noise. So the users only see 48, and unlike Fujin Q, which had a similar architecture, so you can't use that core for compute, although you can theoretically, the operating system prevents it. So we got near Xeon class integer performance on V8 compliant with all the architectural standards. So that's one way of looking at the processor, but the other is it's like an accelerated GPU-based machine because it has all the streaming memory features. It's not like we have the GPU separately, but each of these little cores embedded in the chip actually have architectural features to much like GPUs, to stream data, pump data in and out, and that's really what's making this chip behave. Has sort of like a two-phase, dual-phase behavior. It can behave like an integer core, integer-centric core. It can also behave like a streaming core. And also add reduced data formats like 1 byte. So you can actually compute 256 8-bit integer operations with 32-bit accumulation in one cycle. So if anybody out there has a very interesting integer-based algorithm, not just in deep learning inference, but things like any of the search algorithms or like string matching algorithms, so forth, and you can exploit this integer feature, then this chip will really boost performance by a significant amount over traditional processors. And we retain bytes per flop, about 0.3, 0.4, which is like order of magnitude, nearly order of magnitude better than, let's say, Skylake. And here are some of the detailed specs. I won't go into details here because it takes too much time, but basically this describes the features. So we look at the architecture at the chip level. It's not very different from traditional machines. So it has, I'm sorry, it's a little bit mixed up here, but it has 2 integer units. Also, it has 2 integer address calculation units. So it has give you 2 integer address calculations and 2 integer multi-purpose operations in one cycle. It also has 2 floating point pipes, which can do 5 and 12-bit times 2 vector operations per cycle. So if you look at this architecture, you might think it looks quite conventional. But actually, underneath the core, all the cores are connected by crossbar. Unlike let's say Xeon Phi or Skylake, at the CMG level, it's a crossbar and connecting the cores. And then we have the L2 cache, which is shared. So it's like L3 and Xeon, but it's L2. So bandwidth here is huge, unlike the L3 cache. And then with the memory controller, it connects directly to HBM2. And there's also network on chip interconnect. So if you look at here, the TOFU and also BCI controller are directly attached to the cache covering ring bus. And this allows network operations, advanced network operations like cache injection, which I'll mention later. If you look at the bandwidth numbers here, again, if you know, again, architecture type, you can see here you get enormous bandwidth, enough to, sufficient to sustain a single cycle load from L1 cache all the way up to 1024-bit worth of SIMD lanes from L1 to the DLUs or store, assuming FMA operation. Although unlike Skylake, you cannot overlap this. So Skylake's actually a little bit better in this regard. But to the L2 cache, which is shared, unlike Skylake, which L2 is exclusive, we have half the bandwidth. So communication between the cores actually can exploit this enormous bandwidth, 115 gigabytes or 57 gigabytes. So communication between the cores is really, really fast. And then the L2 cache directly connects to this 150 gigabyte times 2 ring bus. And also 256 gigabyte, you get connection to HBM2. So you get quite a bit of bandwidth within the chip. And also, it's not described here, but all these cache transactions are asynchronous. Unlike Intel, where the cache transactions are synchronous, these cache transactions are asynchronous. Yes, asynchronous cache. And so that allows outstanding memory operation to be streamed through. So very much like a GPU. And that's how the memory bandwidth is sustained. Memory loads, like we do stream, memory load stores have sustained bandwidth that would saturate, that it would even saturate the HBM2 bandwidth. And this really shows in the performance, ignore the flops because flops is no longer important in modern days. If we do a stream triad, for example, you get almost the same, these two chips, V100 and HFX, essentially use the same HBM2s. And you can see here that you both get similar stream triad values, which is almost like 80% in terms of stream triad, which is like more than 80%. And contrastingly, Intel Skylake, of course, gets 80%, 80%, but it's only over 127 gigabytes. And also, network on chip, you get 40 gigabytes per second injection, which is less than the NVLink link on a V100. Oh, but this is global. This is across 100,000 chips, whereas this is localized to just 8 chips on the V100. Beyond that, you have to use InfiniBand. So it's pros and cons, but you can see that this enormous bandwidth is sustained, even though it's a standard CPU. This enormous bandwidth is sustained, and also you get very good gigaflop per watt due to the power saving designs. So you can see the numbers here. I'll skip over, but we see quite a bit of speed up. And and also for power saving features, we added lots of monitoring of power saving. So in fact, what we can do is to explicitly turn off compute units when they're not needed. For example, when you're doing stream processing without doing over regular meshes, you don't need to do considerable address calculations. So then you can turn off the energy units and just let the data stream through. Also, you may not have to have all the floating point units because you're memory bound. So then you can turn them off too. Or if you're doing compute bound jobs, you can tune down the memory controller. So there are a lot of these knobs, power knobs here and there on the chip, and these can be controlled explicitly. And also, of course, the entire chip is designed with extreme cognizance for power efficiency. I mean, very, very low voltage. In fact, the chip is, you can't really crank down the voltage further. You don't even try that because the chip is operating at minimal voltage. that you can have in order to retain the SRAM SRAM state. And we are that low in a reliable manner. Also, when you have a machine that's more than 100,000 nodes, reliability is important. And this is Fujitsu, companies like Fujitsu where they've been building the mainframe for the past 50 years. Their RAS features are second to none. And what ASIC-FX has, as opposed to commodity chips, is all the RAS features that only these mainframe grade chips have. It was also there for K, and most except for just one feature was carried over to Fugaku. One was just too impractical, so we said we'll do less software. But there are many error checks that are being done. There are lots of instruction retries. There are hard recovery features, dynamic, etc. So it's a reliable, very reliable machine. For Tofu, I'm running out of time. We can this 6-dimensional torus, but you think of this as a 3-dimensional torus, and then you have this that's very lopsided, meaning that the 3 dimensions of the torus is huge. It spans the entire machine, and the 3 dimensions are tiny, so it's uneven. But still, it's a 6-dimensional torus and allows a little bit more flexibility compared to full 6-dimension. But it's a little bit, gives us a little bit more flexibility with respect to resilient routing and more congestion control compared to a straightforward 3D torus. BlueJean, IBM BlueJean also has the same similar feature, although it's 5D. They only have 2D on the smaller dimensions. But the effects are the same. So actually, this was a carryover from both Tofu 1, FX K Computer, FX10, and Tofu 2 and FX100 and Post-K. But it's a new version. And what we have done compared to the K is to it's basically very similar. But because it has a network on chip, we hook up the network onto the network on chip, which is a coherent network, fast coherent network. And also we added the D and DMAC to cover all 6 directions. So basically we can do transfers to all 6 directions at the same time, simultaneously, compared to FX100 or K, which only have 4 DMACs. And this is actually utilized quite significantly in collectives optimization. So Fujitsu has a set of research. It's primarily due to them that they have the spanning tree based collective communication optimization, which makes actually the latency on these, although being a huge machine, is actually very good. So the Tofu D is we get injection bandwidth of about 40 gigabytes per second theoretically, and you can maybe some of you who are keen to have a look at charts that it's been a degradation from Tofu 2, which is FX100. The reason being that we really have to save power, and that's a lesson learned number 1, that we're going to be really well, I would say hosed, or will be really critical in the next generations, because the power of the interconnect will start overwhelming the compute power unless we do something about this. And we already are seeing this with Fugaku. And the latency is actually reduced. So between the 2 nodes, depends on the CMGs, but it's about half a microsecond per latency. And cache injection actually contributes. We can inject all the way to cache to level 2 because it's all cache coherent on both sides. And although the nodes are not cache coherent, but the network is. So this contributes to dramatic reduction in latency. And we do get quite a bit of efficiency. We get about 93% efficiency on Tofu. And as I said, for this is a measurement on the K, so this is a little bit older figure, but you can see that Tofu basically scales significantly all the way up to almost full injection bandwidth capacity, even up to 50,000 nodes, almost the full scale of the K machine. We can sustain 17 gigabytes per second around that. If you do the node level injection bandwidth count, that's about 17 gigabytes per second, which was the theoretical limit on K. So expect on the Fugaku, this 38 gigabyte per second injection number will also be realized throughout the entire machine for any collectives like all reduce. Okay, and what we do is to have 58,000 nodes. So it is an exaflop machine in certain precisions, like single and half precision. And I already said about the Green 500, so I'll skip that. I'm sorry, duplicate slides. We do meet all the target application speed up numbers requirements. And this 3 times speed up carries across not just for LIMPAC, but for all the major, I would say, applications, bandwidth bound ones, regular applications. The one on the left-hand side are all the well-known open source applications. So, lesson learned from here, all these run on Fugaku without much modification. And also, both performance-wise and also in terms of power efficiency, this is comparing 2 chips to 1 in terms of absolute performance, and this is comparing power efficiency. And the gray bar is Xeon, and the red bar is A2FX. And you can see in both cases we're about 3 times superior across the board. And the software stack is on the left-hand side, you'll see quite standard HPC ones. We have multiple compilers. The operating system in our case is Red Hat Linux Enterprise, and it runs without modification, so no special patches for A2FX. It's just a standard ARM server. Think of this as a big ARM server, no special patches, just. But also we are integrating cloud and AI software stack. And again, all of them run without a hitch, except for AI software, AI deep learning software stack, which we really had to work to optimize. And today I'm running out of time to describe that. Give me a few minutes, I can go over a little bit of that. So it's this talk about converging HPC and cloud and AI software stack seemed to be much easier than people had anticipated. People said, converging these two stacks are hard. But turns out, we're designing this. It turns out, if we have a very generic processor that can handle everything, all the workloads from HPC to AI to big data to everything, and just can run operating systems and have, they run everything standard. Convergence of all these is quite easy. Can run containers, virtual machines, can do everything. And it's already productized. And skip over advertisement. You can buy one from Fujitsu or from HP Cray, and there are familiar ISV apps, many of which you see here today. GrowMax actually is already ported, and so Eric Lindahl's team will probably work on an even better version, but we already have a version of GrowMax, which is quite well optimized. So that stuff also runs well. And we also are working with multiple cloud vendors. So if you give me for a few more minutes, I'm sorry if people have other stuff to do, but if you give me a few more minutes, I'll describe some implications of both AI and some implications of the Green 500, which kind of points to the future. What do you think, Thorsten? Could you spare me a few minutes? Or should I stop here?
Yes. No, if you have time and others can leave silently if they don't have time. So I would be super interested on, I'm sure
okay.
as well.
Thanks very much. So maybe some of you may have heard, we were crowned like #1 on all the benchmark, and this was very important because we claimed we're application first design philosophy. And, so if we were to claim that, we have to be fast on all the benchmarks and not just one. So we're very happy we achieved that. We also had to be several times faster than the top machines, which were pre-exascale, in order to say anything about us being exascale. So again, we achieved that. So in terms of not, so our machine is exascale. In two terms. One is, of course, some precision. We do have exaflop performance. For example, HPL-AI, the new benchmark, we have 1.4 exaflop result. And also exascale in terms of what the speed up we have achieved compared to the number 2 systems, what are now the number 2 systems, which are pre-exascale. Now, skip over a few slides here and get to the Green 500. Okay, so we were number 1 on the Green 500 2019 November, but now we're not. We're like number 4 and number 9. Number 4 for the smaller machine, prototype machine, and number so 9 for the Fugaku, but we didn't have time to optimize, so we're kind of like number 2 and number 3 in that respect. Around number 3 in that respect, but still there's some difference between the two number 1 machines. But the implication here is that it's only 20% difference. So this is a standard CPU. This is a 100, the latest from NVIDIA, and this is one very, very special purpose matrix engine accelerator from one of the Japanese companies, and both score about 21 gigaflops per watt. Only 20% difference, and these have very specialized BLOS acceleration features like matrix engines. But only 20%. So this kind of begs a question: are we start hitting the limits? No matter what kind of architectural smarts you do, you're still bound by the amount of LUs you put into the system, because LUs, because your power consumption largely will be proportional to the number of LUs plus a little bit of power to move the data around internally within a chip. So even with the architectural optimization, which eliminates some of the overhead of data moving around, you can't really be efficient. All the LUs, they use the same, almost the same stuff. So if you have the same precision. So are we already hitting the limits? So the CPU thing, that they were not very efficient, was an artifact of poor design. But when you have a superior design, then it all looks to be quite similar. And 20% difference is not enough to justify not only a new chip purchase, but this also puts a little bit of dark cloud, saying that we're bound by the LU power efficiency, which is not going to prove much because we'll be lithography limited in the coming years. So, increasing the flops may not be a good idea for the next generation machines. But and we're doing some studies to investigate that. It's not very conclusive yet, but I don't have time to go to the details there. Other is the deep learning, and I'll skip over many of the interesting slides, but just to give you a very rapid overview of what we're doing. So. HPL-AI, of course, we are about 3 times faster. So in fact, we didn't have time. We could hit or simulate or projected numbers said 1.9 exaflops, but we ran out of time. And so with that, we'll be about 3.5 times faster than Summit. So that's a pretty good number. And we're also doing some work to translate the result to MLPerf and MLPerf HPC efforts. So we'll see what the numbers will be there. But in order to do this, we need to have HPL-AI is scalable. It's a synthetic scale, it has synthetic scalability. So it's not really training anything or doing any sort of real inference. It's more rather than just matrix multiply as a representative kernel of a convolutional network. So to achieve real AI speed up, deep learning speed up, you really need to scale your training to 100,000 nodes on Fugaku. And there are many obstacles there. For firstly, we need to achieve high performance in basic D and L kernels, convolution kernels and such, or transformers and such. And it turns out that's not very trivial. It's really, the amount of effort NVIDIA had put in to optimize something like cuDNN to be efficient is enormous. And the more we studied it, the higher respect we have for NVIDIA and also Intel, and like company like Intel's efforts to basically achieve optimality out of their hardware, because because for example, if you take a convolution kernel that can be at very odd sizes, and it's very hard to optimize each and every one of them with a generic loss routine. So there are lots of smarts in there in any cuDNN or OpenAI, Open One API deep learning kernels. And what we're doing is to basically port one API over to ARM SVE, and we're getting very good results there. But also we're trying to emulate CUDA. That's a second approach we're taking. Also trying to do this work done with Thorson's group. Have a little bit higher layer to pick the best convolution kernels, the mechanism to do that. We also need to do high performance in data parallel reduction. And Fugaku, it's pretty good. Of course, there are even better ways to do it, improved additional ways to do it. But as a baseline, we have to pick the best algorithm and so forth. So working on that. As we scale to very large number of nodes, obviously you want to train very large networks or train very large data sets, which imply that you start running out of memory, because each Fugaku node only has 32 gigabytes, which is pretty big. But once you have very large networks, you may only be able to do, put up only 2 batches, and that's not very good. So we need better ways to manage memory, and we have multiple ways of doing it. One is to combine model parallelism, which turned out not to be very trivial. And we have new work, Karma, which was done by Mohammed Wahib, one of the guys at our group, and also AST, which will be published at SC20, which does optimized version of memory management, basically, to offload much of the much of the data set onto secondary memory or to other people's nodes. And it's a very interesting work here. If you're interested, I would recommend you read the Karma paper to be published in a few months. And then this whole convergence becomes a problem. If we can scale, we have to have the network converge, the training converge. So we're trying out various strategies, like traditional method, where we try to optimize SGD. But it's always hard, especially with very large batches. And so many people do that, we do that, and we achieve some optimality, but we start hitting the limits at around a few thousand nodes. So beyond that, we are adopting 2 methods. One is to exploit modern data parallelism, but the other is to utilize a second order algorithm, like Kronecker factorization algorithm, which allows us to, at the risk of higher compute overhead and the risk of overfitting, but may give us better convergence. So there are lots of discussion points here. So this is, I'll leave the slides to you. So if you're interested, you can look at all of them, but just one slide summary of what we do. So we have to combine all these technologies from bottom all the way to the bottom. We have to have very efficient kernels. And there are, again, 2 ways of doing it. And then we build up various types of higher level training supplementary algorithms to increase memory, to achieve better convergence, to increase parallelism. There was another work that we discovered that's been done by UT Austin, follow on to our work. This was published last year. But some people at Austin did follow up to do what's called inverse redesign on this KPAC, which is quite could be quite novel. So if you combine all of these, we may be able to achieve 100,000 node scale deep learning training. And we'll see so that we're in the process of doing this working on all of these artifacts and trying to merge them all to achieve training scalability. And the rest are like all the descriptions. And I will, again, if you're interested, you can look at them, or I can ask the questions if necessary. So yeah, so that's what we're doing. And one final word on COVID effort. Sorry, skip over the nutrition research materials. Didn't manage my time very well. Yeah, so one final word on the COVID simulation. So again, getting back to the capability of Fugaku, Fugaku will not be commissioned officially until April 21 because there are still some few bugs in the system, let's say. It takes a lot of effort. I mean, in fact, there are smaller systems, there are Fugaku, smaller versions of Fugaku and other institutions that are already in production. But they're only like, you know, like 20,000 nodes. I'm sorry, like several thousand nodes. We have 160,000 nodes, and that really taxes the reliability and other features of the software. Finding lots of software scalability bugs. It's really interesting, you know. We discover something that works with 80,000 nodes, but when we scale to 160,000 nodes, something doesn't work. No, so there, you know, it's not 1, 2, 8. We learn something every day. But you know, so a lot of these apps are already in place, working to solve the COVID-19 crisis, from drug discovery to droplet aerosol simulations on trains, and also economic and societal simulations. So very microscopic scale to very macroscopic scale. In fact, these results are already being utilized to come up with recommendations on mitigating infections. For example, you know, analyzing you know, what to do on trains, analyzing what to do in classrooms and offices, and we're working in restaurants. We're discovering that some of the existing drugs are very effective. In fact, we scanned over 2,000 drugs that are already can be given out with prescription, well-tested, you know, drugs that's been there since 1950s, administered to humans but for totally different purposes, like how to deal with combat parasites. And it turned out to be very effective in COVID. So we're discovering those types of drugs, and hopefully they can be put to tests soon, or they're already being tested, and they can serve as not only as drugs to prevent people from becoming serious, but also they can be taken as preventive drugs. So sort of substitute or sort of augmenting the vaccines, because vaccines may have side effects, take time to develop, and also vaccines may not be effective for everyone. So people, elderly people, people who work in hospitals, high-risk people, the combination of vaccines and these new sort of side effect-free existing drugs, which can be manufactured, which are already manufactured in bulk and very cheap, may actually solve this transmissions to quickly mitigate coronavirus. So, you know, all these research going on. So very happy that we're making some impact here. Okay, so I'm sorry I have to kind of rush through the last part, but I think I've finished my talk here. Again, thanks for the opportunity. If you have any questions, I can still be online for the next 5 minutes. So please, thank you. Thank you for listening.